Okay, in this video, I'm going to try to just show you how I might go through and solve some of the later problems that are part of the bungee jumping lab for AP Physics. Now, usually by this time, students, by the time you're watching this video anyway, you've already gone through and done the conceptual understanding of energy transformations, and you plotted your force displacement graph, you used the area underneath the curve, found the energy storage just using the graphical method. Then you did this part here where you did some integration and determined that you were probably pretty close, as long as you did a good graph, that you were able to get your energy in that chord fairly accurately, even without the role of calculus. But nonetheless, you've gotten through that. You had to solve the practical. Most people are able to do that fine, get to the point where you drop it, figure out how much chord you need to be able to do this lab, and invariably you always come up short. So whatever your values are here, if you were dropping 6.1 meters and it came up 30 or 40 or 50 centimeters short, then you could go through and do the remaining calculations to figure out how much non-conservative work was done by things like air drag and the chord and so forth. So at that point, you should all be to this point now where you have done the analysis, you've figured out what your non-conservative force is, all that kind of stuff. What I'm going to do is I'm just going to review that portion of it, and then I'm going to show you, importantly, how I might go through to try to apply the full law of conservation of energy to solve this problem here. So near the end of this video is where you'll see I'll go through the solution on how to actually perhaps how to go through and figure out what length of chord you need. So with that said, let's go ahead and jump over to this screen here. And what I've done is I've taken some pictures of the lab that you're working on, and I'll go ahead and just show you how I might go through and solve these things with this here. Now, I'm going to be over on the board here, so the volume is not picked up as well as it is when I'm standing in front of the hover cam, so please forgive there. But here, let's just do the conceptual understanding of this. The bungee jumper starts all with U graph. And that's based on, of course, M, G, and then whatever the H initial is. We know that as they fall, they lose some gravitational potential energy. They acquire some kinetic energy as they fall. The chord is not stretched yet, so there is no elastic energy yet. How much we have of each one depends on where they are with that. Momentarily in a state of equilibrium. Now, that doesn't mean that all these energy values are the same, but we certainly have all forms of energy present here. So we have U grav, we have U elastic, and we have some kinetic energy. And then finally, at the very bottom, we notice that they still have some gravitational potential energy that's present. And so let's go ahead and make that be a little bit smaller portion. So they still have some U grav. They have a decent amount of elastic energy, but not all of that is elastic energy. And of course, that's because we have some amount of energy loss. And I'm just going to go ahead and color that in, each one of these sections. Now, I did not put any of the energy loss into these other portions here, but in reality, the kinetic energy would be less than what we're expecting here. In each one of these spots, just simply because the work done by non-conservative forces is going to slow that bungee jumper's motion and not allow all of it go into kinetic. Okay, so the idea here is, again, you're trying to figure out how big that portion is, that red pie, as you go through and answer these questions. Now, again, I think usually by this time kids have gone through and figured out how to do this, but in the event that you want a quick review on that, I'll show you how I might do it. By the way, this graph that I have here is a typical potential energy graph for a bungee cord, and it's probably similar to the one that you have if you're comparing yours. This model allows me to go from 0 stretch length to probably about 3 meters of stretch length, and then it gives me the potential energy along this area here, sort of as a function of elongation. So very similar to what your graph is here. Let's say that the initial gravitational potential energy of the jumper before the jump was 10 joules. After the average gravitational potential energy of the jumper relative to the ground at their lowest point, let's say that they came up a little bit short, and so they still have maybe 0.8 joules of gravitational potential energy. The cord did not stretch as far as they expected it to, the actual stretch length. You might have said that the cord was going to stretch 2.5 meters, and you would have stored all that energy as elastic, but in reality, it only stretched not 2.5, but let's say it only stretched 2 meters. And so, actually, let's make that be even different than that so I can use this graph. Well, let's say that the actual stretch is only about 1.8 meters. So, therefore, the average potential energy stored in the cord, and again, I'm doing this using this here, so I would get a more accurate answer if I use my actual graph over there. But I see that actually what they stored there was about, let's say that's in the neighborhood of maybe 8.2 joules. Therefore, the mechanical energy loss for this trial, how would I go through and do that? Let's see, if I had 10, and now what I have is 0.8, and I still have 8.2. If I go through and I do that subtraction for this, I see that, what is that, about 1 joule. So what I did was I lost about 1 joule of mechanical energy in that process. And so the average distance the jumper fell, let's say that that distance was, the bungee cord was here, and it stretched some, and they got all the way down to this particular point. The distance that they fell, if they came up maybe half a meter short, maybe it was 5.6 meters was the total distance that they fell. And so the average distance the person fell was about 5.6 meters. And therefore, the average non-conservative force, non-conservative average value would just be the work done by that divided by the distance. In this case, that would be the drop height that they experienced. I take that 1 divided by 5.6, and that value is about 0.2. Okay, now again, these numbers are not going to be the same as what you have. They might not even be even close to what you have, but this is just how you would go through and calculate that portion. Now, what I'd like to do is I'd like to spend some time showing you how I might go through and solve this problem for dealing with the non-conservative force that's acting. Now, you're going to have to come up with a model for how to determine the size of that non-conservative force. I'm going to just skip over all that portion. I want you to do that. And I'm going to say that force non-conservative, I'm going to say for this one, 0.45 newtons. Just going to use that one for this calculation. Now, let's say that I'm giving you a jumper's mass for all trials. Let's just say that I'm giving you 190 grams. And the drop height, I'm just going to do one of these. Well, let's say one of the drop heights is 5.1 meter, and the other one maybe 4.2 meters. I don't care which one we look at, but let's go ahead and look at how I would go through and solve this problem using this much mass, this much height, and this much non-conservative force. Let me show you how I'd go through and do that. Okay. The main equation for conservation of energy says delta U plus delta K is equal to work non-conservative. When we solved this problem originally, this term was 0. The work non-conservative, this particular term was 0. But now it's no longer 0. In this case, now it's going to be we're going to have a non-zero value due to the fact that there's non-conservative forces doing work. So let's go ahead and just be explicit with our work here and show you how you might go through and just use this equation to solve for the new length. Delta U. Delta U can be both change in gravitational potential energy and change in elastic potential energy. Now, kinetic energy, we know that delta K for the jumper is 0 from beginning to end. There's no changes in the kinetic energy. It starts at 0 and ends at 0. So these two things here would end up being equal to W and C. Let's be very explicit now with this. MGH final minus MGH initial represents the change in gravitational potential energy of that jumper. For this problem, we're going to allow them to go all the way down to the ground, which means, or down to the 5.1 meters, which means that this term, MGH final, will be 0 when we design it to take into account the non-conservative force. So that term is 0. The MGH initial, of course, represents the amount of mass held at the 5.1 meter height. And so that's not going to be 0. Plus, U elastic. Well, I'm sorry, the change in U elastic. Well, it started at 0. We didn't have any energy stored in the core to begin with, and it finally went to a value of U of some X that we're still going to have to figure out. We don't know what that is yet. We're going to try to do that, and we're going to figure out what this value is from our graph, and I'll show you that in a moment. That is equal to work non-conservative, which is the force of non-conservative, minus 0.45 newtons. And that's going to be acting over, we're going to assume that they fall the full 5.1 meters. So that's going to be acting over 5.1 meters. This represents energy loss. I'm just going to solve this equation for U of X. So U of X represents then this value. Let's just do that math quick. The negative 0.45 multiplied by 5.1. This value here is negative 2.295 joules. And then I'm going to add to that plus mgh, which in this case would be 0.19 multiplied by 9.8 multiplied by, well, we're going to let that jumper go all the way down to the ground, multiplied by 5.1 meters. And this will give me now U of X, how much potential energy I'm going to expect to actually store in that cord, because I have some non-conservative forces doing work. And so let's go ahead and do that. So 0.19 multiplied by 9.8 multiplied by 5.1. That number is 9.5 here. If there was no non-conservative forces acting, then I would come over here and figure out how far this thing would go. 9.5 joules is around here. I would say, that cord's going to stretch, 2 meters or so. But we know that it's not going to stretch that far because there is non-conservative forces acting. What do I actually get for my U of X? It's going to be reduced by that ideal value by 2.295. So I'm going to take that, subtract from that 2.295, and U of X is going to end up being, if everything's done correctly, U of X is only 7.2 joules. What that means is the cord did not stretch as far, or will not stretch as far as I'm expecting it to, because I have to take into account the energy loss that's being done by the non-conservative forces. So let's see, 7.2 joules coming up here. And again, if I actually have the graph in front of me here, I would be able to get this more accurately. But I come over here and say, well, that cord is really only going to stretch about, let's see, 1.6, 1.7, maybe about 1.68. So that means delta L, how much it actually stretches here, about 1.68 meters. That's what it should end up stretching to store that much energy. Now, of course, it would have been a lot longer. It would have stretched a lot further if we were at the full 9.5. And just for illustrative purposes, if it really was going to stretch the entire 9.5, that cord would have stretched almost to a full 2 meters. Okay, so, but it obviously will not, simply because we're losing some of that energy. This number now becomes the value that I'd use to determine the inelastic cord length. Let's say we're going to take 5.1 meters. We're going to subtract from that the relaxed length. So let's go ahead and put that down. The relaxed length for this one, let's say the relaxed length was 1.7 meters. We're going to subtract from that the delta L, which is how far that thing's going to stretch, 1.68 meters. And then whatever the hardware is for your jumper, I think for you guys it was 0.19 meters. When I go through and do all this, let's see, 5.1 minus 1.7 minus 1.68 minus 0.19 tells me I need that cord to be 1.53 meters long. That's going to be longer. Yeah, that's the inelastic portion for that cord. That's going to be longer than if I assumed mechanical energy was conserved. And so this is the value then that I might, if I'm going through and using this value for the non-conservative force, trying to stop that 190 gram mass object after falling 5.1 meters, I would then take that inelastic cord and put it at 1.53. That might then take into account the loss of mechanical energy due to non-conservative forces to try to get them as close as possible without hitting. Now, if I'm going to try to err on the safe side, instead of putting it at 1.53, I might cheat that a little bit and say, well, I'm gonna take off a little bit, maybe put it at 1.51 or something along those lines, so that I make sure I don't hit the board. Okay, so again, I wanted you to see a worked out solution to this in the event that you struggled a little bit with solving the practical when I have non-conservative forces that are not zero. This equation here is foundational to the law of conservation of energy. And if we use this anytime we're having energy changing from one form to another, and it's also valid when we have work done by something external that could either add or subtract energy, mechanical energy to that process. So in the event that you're watching this video, I hope that you find this helpful, and good luck with the bungee jumping, and hopefully we have some good successful trials.